Hi, my name's Dan, and this video is one in a largish scheme of videos, about 55 altogether. Okay, so that's quite a big number, which chart the progress of using a digital electronic simulator to go from basic logic gates all the way through to a working 4-bit CPU. So it's quite a grand scheme that I've got. There is a roadmap of where I'm going with that in the description down below. There's also a link to the software that I'm using to simulate this called Digital Works. We're not actually going to use that in this video or in any of the videos in this shorter series within the larger series. So this shorter series is designing the CPU, making some design decisions, or basically telling you about the decisions that I've previously made, but explaining them and kind of going through the process of that. It's all very specific now. Some of the previous videos were quite generic, but everything is getting now very tailored towards our specific 4-bit CPU that we're going to create in Digital Works. And I hope you're playing along with me and using the software to actually create it. But this shorter series is within the larger series is all design thoughts. So we're not actually firing up Digital Works at all in this playlist and not in this video at all, of course. And in this video, we've come to the point now in the CPU design where we're going to design the opcodes. So that's the codes that tell the CPU what operations to do. And there are various things that we're going to want it to do, and we'll talk through that. And by the end of this video, we'll have a complete list of opcodes. So it's a 4-bit machine. So this means that actually we've only got 16 opcodes to play with. And in some ways this is good, but in some other ways this is very limiting. Quite often for the minimum that people tend to design is 8-bit, which gives you a huge amount more than this. The limitations of the simulator, the Digital Works software, means that an 8-bit is quite difficult to achieve. But 4-bit is definitely achievable. And actually, the size of what you're making is considerably less with this. So this is my justification of the fact that I'm doing 4-bit rather than 8-bit. It's less work for you. It's less confusing for you, hopefully, and it'll work, or it will if you do it right. Okay, so let's crack into the opcodes. We've already, in previous set of videos, looked at the ALU, and which is the arithmetic logic unit, which is the thing that actually does some calculations for us. And we actually designed that around the potential for some opcodes. So let's give you a reminder of that. So out of our 4 bits, bit 3 is the most significant bit, so that comes on the left-hand side. Bit 0 is the least significant bit, which comes to the right-hand side as you write it in the normal way of writing a binary number. So bit 3 tells it whether it's going to do add or XOR. Bit 2 is our C-in, so it's called that because it's a carry-in to the adder. Bits 1 and 0 choose the second parameter, so A is a fixed parameter, and B is our chosen parameter that we send in, but actually it can be, the ALU can either pick the B or do various other things, and this is the choices. If bits 1 and 0 was 0, 0, then it actually uses a hardwired 0, 0, 0, 0 constant. If it's 0, 1, it uses a hardwired 1, 1, 1, 1 constant. If it's 1, 0, it gives you the B that you've fed in, and if it's 1, 1, it gives you the inverse of B that you've fed in. And there are various mathematical reasons why we chose those. Excuse me. But this gives a complete capability, as is shown in this table here. So we've got the opcodes on the left, and what I'm going to do is I'm going to go through each of the rows in turn and explain what the combination of the 4 bits will actually give us if we're using our ALU for this operation. So 0, 0, 0, 0 gives us A add 0, so the output is A. So that's pointless because it does nothing to it. 0001, so that gives us a, add 1111 with no carry in. This gives us actually a minus 1. It will flag the carry out, but it's useful as a decrement. So we've got to keep that one. The next one lets us to add a to b with no carry in, so a plus b is pretty useful. The next one gives us a minus b, and because there's no carry in, it's actually a minus b minus 1. Less useful, so we're actually going to reject that one out. The next ones, so what? Now the next four are a repeat of the first four, but they've got the carry in. So instead of a, we've got a plus 1. So that's useful, that's an increment. Instead of a minus 1, we've got a, so that just gives us the same as the input. There's no point in having that one. This one is a plus b plus 1, which is a bit unusual. If there were specific uses we had for it, we might keep it. But we can actually achieve the same thing just by doing a plus b followed by that result plus 1. So we're not going to do it natively. This is the one this is why we've got the inverse b in here, which is if you add a and inverse b and put the carry out as 1, you actually get a minus b. I'm not going to go through the theory of why that is, but trust me, you do. So that's one that's worth keeping. So the next 8 are all XORs rather than add. And in fact, the C in, the carry in, has no effect on the XOR. So it's just the XOR and then whatever we're choosing on the B. So A XORed with 0000 gives us A as the output. Again, nothing happening there of any use. A XOR with 1111 gives us inverse of A. Well, we might want that in some circumstances. So we're going to leave that one in. AX or B is hugely useful and important. The result is always going to be 0 if they're the same, but if they are the same, then it gives us the Z flag goes up, and it allows us to ask the question: is A the same as B, and to have some information come out as a result. And the next one is the question is A the same as inverse B? And actually, there may be uses for that mathematically, but I don't know of them. So we're going to ignore that one. And then the next four actually are exactly the same as the four above, because the C in has no impact, so they're just a repeat. So what I'm going to do is I'm going to leave in the ones that we're actually going to use, which is 6 operations that we talked about when we made the ALU, and we're going to see what gaps we've got left. So there we go. We've got our 6. We've got A minus 1. We've got A plus B, A plus 1, A minus B, inverse A, and compare. And that's a very useful set, given the minimality that we used in the ALU. This is really quite a clever thing in terms of what we're able to produce as a result. So we've got the rest of these opcodes we can use for everything else that we want to do. But what else do we want to do? So we want to move data around between registers, and we want to do jumping around in the flow of the program, so we can interrupt the program flow. And we want to halt. So we want one of these instructions to be stop. That's it. Everything's finished. Okay. So let's get into the moving data. So I guess you think kind of the maximum that we could do maybe would be every register to every other register. Actually, there are things in here that we don't want to do. So we don't need to read from the memory address register. We only ever want to write to it. It's not something that we're ever going to want to extract the information from. Similarly, we don't want to write to the ALUX, which is the output from the ALU, or for the ALU flags, because they should only ever be written by the ALU itself. So we want to read from the ALUX, and we're going to use the ALU flags for the jumping. So we don't actually want to have no need to read from those either. PC, which is the program counter, and op, which holds the operation that's currently being used, and data will look after themselves somewhat. Data's a bit of a strange one because we will read from data and we'll use it in another way as well, but we won't write to it. And basically this is because PC is to do with the flow of the program, and we're only ever going to use that when we're doing when we're moving the program on, or when we're doing jumps. So we don't need um, register moving uh, instructions to do anything with PC. Similarly, op is only ever going to be the data that we've read out of the memory, and we don't want to do anything other than put it in the op register and then use it to disambiguate what else we do to uh, for that. So the control unit will read the op, but we don't need to move that about anyway. So it's only data that we'll need to look at, and we'll show how that's going to happen. We do need to be able to read um, read from memory locations and write to memory locations. Well, actually, that's going to be using data because it uses data as the address, and then you get the data from the memory data register, or put it into the memory data register. We don't have the opcode space for all of the rest of these. Um, so we can't do everything to everything. So what we're going to do is we're going to use the A register as a go-between. So basically, we're going to allow data to go into A from everywhere and from A out to everywhere that is reasonable. So here's our proposed list of data moves, and we'll kind of walk through how this covers hopefully everything that we're going to need. Copying A to a memory location, copying A to B, copying a memory location to A, putting a specific number in A, and that's another use that we'll use of the data register, is to put in a specific number as part of an instruction, and so I want to store this in A. So this is how new numbers become part of the system of what's going on. Copy ALUX to A, which is the output from the ALU, and copy B to A. Do we need all these? I'm not quite sure if we absolutely need all of them, but we certainly need most of them. I think we probably do. I think we've got this down to a minimum size of what we can have. So let's have a check that actually all the data transfers we might want to do are possible. So here's a table which gives us from, and I've started with a specific number, so that's actually hard-coded data, from a memory location for A, B, and ALUX. And actually, I'm only using kind of 3 registers here, plus the number, which is actually data, plus the memory, which is actually using the data as a memory address. All the others are kind of in use elsewhere, but not as part of the general shuffling around of stuff that you might want to do. And if you don't trust me on that, I'm sorry. So anyway, we got the froms down the left-hand side, and we've got 2 on the across the top. So for example, the top left is from number to number. That's one we're not going to want. From the next one across is from number to memory, etc. So the ones that we're not going to need is most of them where it's from itself to itself. So from number to number, from A to A, from B to B, from ALUX to ALUX, not needed. From memory to memory could be needed. You might want to copy a number from one memory location to another. So that's why that one's been left in. And also, you never want to write 2 hardwired data number, and you never want to write to the ALUX. So the only twos that are valid are memory A and B. Okay, so here are the ones that have been proposed previously. We've got the 4 that move data into A and the 2 that move data from A. Now, I'm going to talk quickly about the notation that I'm using here. There's a thing, it's been formalized, and it's called Register Transfer Language, or RTL for short. And all it is a shorthand showing movement of data from one register to another. And it's a little odd to get used to start off with, because it maybe feels backwards, but there is a good reason for it being this way. So the thing that is receiving the data is on the left. Then you've got an arrow. That's what I'm using. This less than sign on the dash to indicate an arrow. And then the thing that the data is being copied from is on the right. And so you can't say, so say this top one here is A arrow data, but the arrow goes from data to the A. And you don't describe this as being copy A to data. It's copy into A from data. Okay. Now, when I first met this, I thought it would make more sense for it to be the other way around and for this to be data arrow going to the right, A. Okay. My justification of it, I don't actually know if this is the reason why it evolved in this way in the first place, is that this looks very like a programming language, in that if you wrote in a programming language, if you had a variable A and a variable data, you would write A equals data, and that would take the value of data and put it into A. And this is the same way around as if you were in a programming language. The other thing to add here is that we've got something here in square brackets, and that means not the actual data that's in MAR, which is the memory address register, but the data in the location indicated by MAR. Okay, so the square brackets means you need to work out which memory location this is going to be. So MAR pretty much will always be inside these square brackets, and that means we're going to use a memory location. So quickly talking through these, down from the top in the column that's got A at the top, you've got data. So that means a hardwired number. So a hardwired number will actually go into the data register. And so that means you need to move data into the A register. And from a memory location, actually the location for the memory will be held also in the data register, but we'll come back to that in a second. We move it into the memory address register, and then we copy from whatever address. So we do the read from the memory and then copy from the memory data register to A. So a two-part operation. Then there's the skip, because you don't want to do A to A, and then there's B to A, and then there's LUX to A. And then at the sides, in this kind of cross shape, we've got the other way around, A to a memory location, and on the right, we've got A going into B. Okay. So the ones that we haven't got covered are the ones where we've got holes at the moment. And actually, all those we can do using two of the other operations that we're proposing. And I'll just fill them in the table. I am not going to talk through them, but I will just do the top left one, which is going from number to memory location. So in order to do this, the number's held in data, in the data register. So you move the data into A, and then you move from A to the memory location. And this is why the proposed ones in black form a cross shape, is because between them they cover all the movements that you might want to do. As I said earlier, it might have been nicer to have had all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 of these implemented as opcodes, but we just don't have the space in our number of opcodes to be able to do that. So we're having to make some compromises here. Okay. So let's go back to our list of data moves. We've verified that we can hopefully do everything that we want with them, even though things might be long-winded. And I'm going to turn them into two lists. One of the lists is data from A to somewhere, and the other one is the from somewhere to A. And I've actually lined these up as well. I've moved them around so that the top two are A to a memory location and A to B, and they have their opposite of memory location to A and B to A. And in fact, this kind of means we can use a set of numbers that are down below here. This is somewhat coincidental that this comes out somewhat designed. But we've got 1000 and 1011, which are so the second bit 2 here is 0. So they're all with bit 1 being 1. Bit 2 being 0, we've got 2 of those. And bit 2 being 1, we've got 4 of those. And so we wanted 2 in one direction and 4 in the other direction. And we can actually set it up as follows. So bit 3 is not used in determining what a memory transfer does. Bit 2 tells you if you're going from A or to A, and then bits 1 and 0 define the other register that's in play that isn't A. So 00 is a memory location, 01 is data that's hardwired, 10 is ALUX, and 11 is B. So we can slot those in to our list of opcodes, and I've just put them in blue. And all I've done is I've rather than write them out, is I've used this register transfer language again. But I've done something sneaky. You might have noticed that instead of saying MAR inside the square brackets, I've actually written data, because what's actually going to happen with the operation is that we're going to hold the data separately to the operation number. So these operations are going to be able to have extra information, which is going to go into the data register. And from that data register, that will then go to the MAR, the memory address register, when it sees that that's what needs to be done. And then the contents of, so for the top blue one here, the contents of the A register goes to the memory location that was previously held in data. Okay, so it's a couple of stages to actually make that happen, but there we go. So that is our data transfer, our register transfer operations dealt with. We've done them in the bottom half of the table. So what else do we need? We need jumping, and we've got a little bit of space here for a couple of jumps. In fact, we're going to throw in 3. So we want an unconditional jump, which is quite useful if you want a program that does an infinite loop. So this will loop over and over again. Or if you want the kind of loop where somewhere else you've got a condition and it jumps out of the loop. So that also could be done. So infinite loops, unconditional jumps are useful, but also conditional jumps are useful. And the 2 things that we're going to use for our conditions are actually the flags from the ALU, which are the Z flag, which will go high if our output is 0, or if our number is 0. And we're going to also have a jump which is dependent on the carry out. It could be useful. We just about have the space to do that. So we're going to do jump if the Z flag is not set. So we're going to jump if the result is not 0. It's somewhat arbitrary as to which way around. I think it's more common to use not 0. Jump if the C flag is set, though. So that's more like an exception at this point, where you're jumping out if something has potentially gone wrong. Okay, which gives us 3 things we want to do as jumps. I've just put the codes against them that we're going to use. It kind of works as a sort of bit pattern, but it's stretching it a bit to describe it. The unconditional jump has got bits 1 and 0 are both set to 1, and if you put one of them to 0 in the conditional jumps, then that could indicate which thing is being used, but it's stretching it a bit to actually describe it as that. But I'm going to chuck those into the table. So we've got the 3 in green there, which is the JMP for jump, JC for jump if C set, and JNZ for jump if Z is not set. And that leaves us 1 left over, which is good because we need to put halt in, which is the last thing that we needed. It has been mostly coincidence and very, very slightly design that the halt opcode is 0000. But that's actually really useful, and it's fairly common for this to be the case, that you use zeros as a halt code. And the reason for that is because what you tend to do when you put in the opcodes for the program in memory is wipe the memory first, turn it all to zeros, and then you put your opcodes in. And then you don't need to remember to put a halt in, because your next one will automatically be 0. So when you get to the end of your program, it will stop, and it won't. If 0000 was something else like add A to B, then it'll just keep doing that over and over and over again. So it's very useful having halt as 0000. Okay. So the last thing we're going to do is I've got a column on the right hand side here on this table that I don't know if you noticed was there and is not used. I'm actually just going to label each of these operations by which group of operations they're in. They're coloured as well in this table. So black, we've got the ALU operations. We've got the jump operations, which are in green. We've got the register transfer operations, which I'm going to call reg as a group, which are blue, and we've got halt, which I've got as red. And one of the things that the control unit is going to do is, in fact, pretty much the first thing that it does when it gets the opcode is work out which group of operations it's in, and then it will work out from there which particular operation it's going to use. So that's it. We've gone through, I've rattled through it fairly quickly. I hope you've managed to follow it. If there's anything that you're not sure about, obviously go back and replay it. But we have, as a result, now got a complete set of 16 opcodes. And these opcodes will cover some basic mathematical things. They cover moving data around so we can get stuff into place to do the maths that we want. We've got some program flow, we've got conditions, so we've got sequence, so we've got selection and iteration. So we're able to go round and round in loops, we're able to make choices, and we've got halts. And this is pretty much everything you need to be able to make a programmable CPU. It's very minimal and it only just really fits into a 4-bit CPU. But it's good, it does. So we're going to move on from here into more talking about what the CPU hardware is going to be. But that is it from me for now.